All right. Hi everyone. Thank you for coming tonight at a bit of an unusual time. So today we're having Harris Aziz as our speaker. So he's an associate professor at UNSW, so University of New South Wales in Sydney, and he's leading the algorithmic decision theory group there. He was also the founding director there of the AI Institute, which is like a huge institute that has over 300 faculty members. And so he does research in AI in theoretical computer science, in mathematical social sciences, especially in computational social choice and in algorithmic game theory. And so today he's going to tell us about some of his work on fairness, and he's going to talk about like best of both worlds fairness. So Harris, it's all you now.
Thank you, Juba. It's great to be part of the seminar series. My research is primarily focused on fairness aspects, whether it's voting, matching, allocation, or other collective decision-making problems. So it's wonderful to be at a seminar series which focuses on fairness. So this particular talk is on a paradigm called best of both worlds fairness, and it's a 1 hour long talk or slightly shorter. But my main aim will be to promote this paradigm and to encourage you to explore this paradigm in your favorite research domain. So just to give credit to my wonderful co-authors, some of the work that I'll present today, it's based on joint work with Rupert Freeman, Nisag Shah, Rohit Vesh. Then another set of co-authors was Adi Ganguly, who was my undergrad student, and Evi Micha, who many of you might know from her research. She's based in America. And then there's one piece of work which is based on our group members at UNSW Sydney, including Jin Hanglu, Mashpat, Suzuki, Jeremy Wolin, and Toby Walsh. So uh, the main thing I want to promote here is this best of both worlds paradigm in fairness decision making. And the idea behind best of both worlds paradigm is that often it's not very easy to achieve fairness ex post, especially when you have outcomes which are deterministic and integral. But the goal is to simultaneously achieve fairness properties both in expectation, ex ante, and also at least approximately fair ex post, that is after the coin toss is realized. So in this particular talk, I'm going to discuss this paradigm in the context of two favorite decision-making domain that I work on. One is allocation of goods, and another is what is called committee voting, or also called multi-winner voting, where you vote to decide and select a set of candidates. So let's begin with some work on best of both worlds fairness in the context of allocation problems. And I expect this is an expert audience in fairness. So many of you might have worked on typical allocation problems where you have a set of items, you have a set of agents, and the goal is to allocate those items among the agents in some kind of fair way. This is a very simple example where you have two agents and three items A, B, C, and each of these agents has some additive valuations or utilities over these individual items. So for this particular talk, I'll focus on a simple domain where people have additive valuations, which means that if, for example, agent one gets both A and B, then its total utility is going to be 5 plus 3, which is 8. So the goal is to allocate these items among the agents, which can be done in various ways. And one extreme way of doing this would be to give all three items to agent one. And this is represented in this matrix form where agent one gets 1, 1, 1 for each of these items, which means it gets all of these items completely. Obviously, this is not a very fair outcome because agent 2 did not get any item. It would be envious of agent 1. And in fact, for most reasonable fairness definitions, you would say that this allocation is not very fair. However, if you toss the coin and half the time you're giving agent 1 with probability half, you give agent 1 all the items, with probability half, you give agent 2 all the items, This outcome is, at least in terms of expected utility, it seems quite fair. So it's fair from an ex ante point of view. But again, when the lotteries realize it's not uh, fair. So the idea behind this best of both worlds paradigm is that not only do we want to achieve fairness ex ante, which we have done in this case, but we also want to make sure that the ex post outcomes are fair as well. So that's the idea behind what is called this best of both worlds paradigm. So typically, when you allow randomization, ex ante fairness is relatively easy to achieve. For example, you could take each item and with equal probability, you could give it to each of the agents. That is ex ante fair. Everybody in expectation is getting 1/n of each item. So you can easily achieve it. On the other hand, ex post fairness is slightly more harder to grapple with, and many interesting relaxations have been explored in recent years. One particular relaxation, which many of you might be aware of, is what is called entry freeness up to one item, which I will discuss soon. So the idea behind this particular paradigm is that how to simultaneously achieve ex ante fairness and ex post uh, fairness, at least approximately. So I just want to credit Hervé Mullah and his co-editors who invited me to write this sort of a blue sky. It has a bunch of blue sky chapters, which are very short, where people have explored various aspects. And this in 2019, I was exploring some of it in this book chapter, but I did not really. I've been working on probabilistic voting quite a bit, but I did not really explore this best of both worlds paradigm, especially from a technical sense, as much until I saw a very nice paper by Rupert, Rohit, and his co-authors and Nisag, which came out a couple of years later. So let me just explain how the ideas developed. So firstly, let me just explore what the setting is, which I'm going to discuss. Agents have additive positive utilities over indivisible items. And the outcome that we after is some randomized outcome, which is either an explicit or an implicit probability distribution over integral allocations. So the challenge is to simultaneously achieve good ex-ante properties, and also we'll consider some typical efficiency concepts such as Pareto optimality. So firstly, I won't go into technical definitions. It's expert audience on fairness. So we are going after one of the gold standards in fairness, which is envy fairness, which simply means that no agent envies another agent or does not want to get somebody else's allocation instead of their own bundle. Also, simultaneously, we explore Pareto optimality, which is one of the minimal efficiency criteria in mathematical economics, which requires that there exists no other outcome in which all agents weakly prefer and at least one agent strictly prefers. So considering that we are in this additive utility world, we are after this envy fairness and Pareto optimality, and immediately we arrive to this observation that you can't allocate items among the agents and get envy fairness. For example, if there's just one item, how do you achieve envy fairness? One way could be that you don't allocate items, right? But then it's not Pareto optimal. So there's already, for very simple examples, there's an inherent tension between these two basic concepts, envy fairness and Pareto optimality. So since we are in this best of both worlds, we will consider both fairness and efficiency, both from an ex ante point of view and an ex post point of view. So here I've listed four, for both ex ante, I have efficiency and fairness, and both for ex post, we have efficiency and fairness as well. So we have four different target class of properties. One is ex post fairness, then ex ante fairness, then ex ante efficiency, and then ex post efficiency. So since we are focusing on envy fairness and Pareto optimality, for ex ante fairness, we immediately focus on ex ante envy fairness. For ex ante efficiency, we go for ex ante Pareto optimality, and same for ex post efficiency, we go for ex post Pareto optimality. If you notice, for ex post fairness, we don't have ex post NV fairness because we already know that you can't guarantee the existence of an NV free allocation ex post. For that reason, people in computer science have resorted to this very nice natural relaxation of NV freeness called NV freeness up to one item, which is abbreviated as EF1. So I won't go into a technical definition of NV freeness. It's a very simple idea. It just means that either the allocation is NV free, or it's the case that anybody who's envious, that person's envy goes away if we ignore one item. So, for example, I am envying Juba for a particular allocation, and I say that Juba got a better.
You probably should not envy me.
Well, this hypothetical allocation, yeah, somehow I feel that it's you got a much better bundle than I did. Then the relaxation of envy freeness in this case would be that as long as there is some item in Juba's bundle, which if removed, I'm not envious of Juba anymore, then that gives you this EF1 requirement. So obviously, if some allocation is EF, that's great. But even if somebody is envious, for example, I was envious in this case, then that envy should go away as long as some item is removed from consideration. So the nice thing about EF1 is that it's guaranteed to
Can
exist.
I ask you a super quick question about a definition? Is it, do you get to choose which item you remove, or is it removing any item?
So EF1 is a weak property, so there must be some item that can be removed.
But there
There's a
only
number
needs to be one. It doesn't need
there
to
only
be
needs to be
removing
one.
anything. Got you. Okay, that's what I
There only
wanted to
needs
know.
to there only needs to be one. Sorry, I didn't put in precise technical definition because I didn't set up notation. But there's also a very exciting, stronger definition, which is between EF1 and EF, which is called EFX, where you require that the NV should go away if we remove any item from Juba's bundle, my NV should go away. So that's stronger. But for our case, we just require the existence of some item in the NV'd agents bundle, which needs to be removed. So what is nice about EF1 is that it can be achieved, it is guaranteed to exist, and there are many nice algorithms or rules which guarantee its outcome. So one is called round robin allocation, which I will explain. The other two I will briefly mention. One is called Lepton et al.'s NV cycles algorithm. And the nice thing about Lipton et al.'s NV cycle algorithm is that not only does it give you EF1 guarantee for additive valuations, but in fact, for arbitrary positive monotonic valuations, it gives you a very nice, efficient algorithm for computing an EFN allocation. Finally, there's one other rule which is called MNW rule of Karianis et al. This is quite an influential paper which further popularized EF1 uh, property, and it recently won the Game Theory Society's most influential game theory and computer science paper award as well. So it's highly cited in the fair division, especially the integral allocation context. So I won't go into too much detail on the latter two algorithms, but round robin or variations or generalization of round robin will heavily feature in some of our slides. All right, so this is the paper that I was mentioning, which was this award-winning paper. And the nice thing, one of the nicest results in the paper was that they identified this M&W rule, which is based on this natural idea of first maximizing the number of agents who get more than zero utility. And among the agents who get more than zero utility, you want to maximize the Nash social welfare, which is the product of the utilities of those agents. So clearly, this outcome of this rule is Pareto optimal. What is not so obvious is that the outcome of this rule is EF1, and that was one of the main contributions of the paper. They show that actually under additive utilities, this particular rule also gives you EF1. So considering in fair allocation, there's always this tension between fairness and efficiency properties. This is a nice example where you have a natural rule which gives you approximate fairness, and it also gives you the most important efficiency property, which is Pareto optimality. But this particular rule is NP hard to implement, and um, whereas there's a very simple linear time algorithm which can give you EF1, and actually I'm going to give you a visual proof of why this particular rule works. So this is called the round robin sequential rule, which is agents are coming in a round robin order. In each agent's turn, she picks the most preferred item that has not yet been allocated. And the nice thing is that this particular rule, which you might have used in your school recess when making school teams or in other contexts, this particular rule, which is intuitively quite fair, it also guarantees this formal requirement of NV fairness up to one item. So let me give you this argument why it gives you an EF1 allocation. Say that J is envious of I, and in the worst case, if that's the case, then I gets the first pick, and it also gets the last pick. So it's getting one more pick than agent J. I'm going to argue why, even if J is envious of I, that envy goes away as long as you ignore one item in I's bundle. So the item that we're going to ignore from consideration is the first item that is picked by agent I, which is this O0 prime. So we ignore that item from consideration. And what you notice now is that the first item that agent J picks is obviously going to be the most preferred item in the whole bundle. That is obviously agent J thinks that that item is at least as preferred as the first item, not the first, but the second item agent I picks, which is O1 prime. Similarly, for any item that agent J picks, it's going to pick that item before it even has interest in the next item that agent I picks. For that reason, you have this one-on-one relation where agent J's one item is more preferred by agent J than a corresponding item picked by agent I. So this is a very simple argument why agent J thinks that what it got is better than agent I's bundle as long as we remove the first item, I prime 0, which was picked by agent I. What is nice about this argument is that not only does it work for recursively balanced allocations, it works for any class of sequences which are called recursively balanced. Now, what are recursively balanced sequences? They are sequences in which no agent has a lead of 2 turns. So at any point, agents have a lead of 1 turn over the other agent. Another way to think about it is that you can think in terms of rounds in which agent I and agent J, one of them picks, then another one picks, you don't specify which one, and then you proceed in the next round and so on. So this EF1 argument works for recursively balanced sequence. As far as ex ante fairness is concerned, I already told you there's the uniform rule where every item is uniformly at random allocated among the agents. That's NV free. Obviously, that's not Pareto optimal, but there are some nice rules in the literature which also give you some kind of efficiency property. So competitive equilibrium with equal income, CI gives you both EF ex ante and PO ex ante. But there are some other rules which give you some very strong versions of EF and also some reasonable relaxations of Pareto optimality. So among these rules, the rule I really want to focus on is this probabilistic serial rule of Bogomolin-Moulin that came out in 2001. And that rule can simply be viewed as what is called an eating algorithm. Let me just demonstrate it. If let's say you have 3 agents and 3 items, agents start eating these items at uniform rate, and at some point they consume all the items. They're always going for the most preferred item. When some item is consumed, they go to the next one. So the probability with which an agent gets a certain item is exactly the amount of time it spends on eating that item. So for example, in this case, agent 1 spent 3/4 of the time on eating item O1. So it's going to get O1 with probability 3/4 and so on. So this is a nice rule and it already has some nice advantages over a rival rule called the random priority rule, which I will not go into that much. Basically, the main contribution of Bogomolai and Molai in that paper was that they showed that probabilistic serial has advantages over this random priority rule, both in terms of efficiency and envy-freeness. Now, what they were not considering ordinal, they were considering not cardinal utilities, but an ordinal model. And in this ordinal model, if you want to translate properties in the way we're expecting in the cardinal world, I'll just mention what these properties are. SD efficiency is a very weak version of Pareto optimality, which says that it's Pareto optimal with respect to some cardinal utilities consistent with the ordinal preferences. Whereas SD envy-freeness is a very strong version of envy-freeness, which means that it's envy-free with respect to all utilities which are consistent with the ordinal preferences. So this rule is giving us a very strong version of envy-freeness and a weak version of Pareto optimality. And it's clear it can't be Pareto optimal because it's simply ignoring the cardinal utility information. So the first time I saw this, obviously best of both worlds or many worlds is applied in multi-objective optimization. But in the context of fairness, best of both worlds fairness, this term was first coined by Rupert, Nisag, and Rohit in this 2020 EC paper, which came out. And that's where some very nice results were presented, technical results around best of both worlds fairness in the item allocation context. So there are many results, but pictorially, some of the results which immediately caught my attention were, one was that they already showed that envy-freeness up to one item and envy-freeness, these two properties which are linked in this green color, they are compatible. They also showed quite a devastating negative example, which showed that X anti-Pareto optimality, X anti-envy-freeness, and X post EF1 are incompatible. So these were two of the main results, but they also had several other results, which I'll mention later. But my interest in this topic was piqued by this paper and also some very natural questions that they either explicitly asked or they arose from that paper. One was that they were using some version of probabilistic serial in that paper, but they asked the question that is it possible to run the probabilistic serial outcome and then decompose it into lottery over EF1 outcomes? That question was open, and there were many other combinations of properties which one could explore and understand whether they were compatible or incompatible. So I later wrote a wine paper the same year, which basically was a very simple algorithm. It can be described in half a page and analyze. Analysis is also not that difficult, which basically uh, took this thing further by showing that you can achieve these properties in green. And one nice thing about this was that it's just combines some very simple natural algorithms which are already used in the matching and allocation literature. In particular, it uses what is called the PS lottery, the same Bogomolai and Boulin algorithm, slightly more generalized version of it, which takes into account indifferences and gives you ordinal Pareto optimality guarantees. And then it just uses Birkhoff decomposition and using some invoking some maximum size matching algorithm. So how does this algorithm work? It's fairly simple. When you have agents, you have items, you can plug in some dummy items just to ensure that the number of items is a multiple of the number of agents. In this case, luckily, we don't have to plug in dummy items, so we just have these two agents and four items. After that, what we do is we run the probabilistic serial algorithm and get the outcome. Now, our goal is that we want to decompose this particular matrix given as R into convex combinations of integral outcomes, all of which are EF1. We already know that in expectation, this particular algorithm is SD efficient and SD envy free. So after that, what we do is we take each agent's allocation and we let successive representative agents of that agent eat exactly 1 unit of the items one by one to get another allocation. So for example, if agent one gets half of A, one of B, none of C, and half of D, then agent one is going to simulate its own eating process where its first representative gets 1 unit of item, then another representative gets a second unit of item. So the first representative agent one is just going to get half of A and then half of B, and it's going to stop. And then the second representative takes the remaining on its behalf. So this is what we simulate, and what we do is we bunch all of these simulated outcomes together to get a biostochastic matrix where you have each agent's representative getting 1 unit of item, and obviously each item is given in total to one agent. After that, we need to do decomposition, and actually we can use just the way we've set up things, we can just use an arbitrary Birkhoff decomposition to get this kind of outcome in which we have this permutation matrices. These permutation matrices correspond to integral allocations, where we don't really care about whether agent one's first representative got a certain item or the second, because it's all going on behalf of agent one and agent two respectively. So we can change this outcome back into an outcome which is only for agent one and agent two, because the representatives were just getting items on behalf of their main agent. And this is it. The algorithm is simple. The main thing is that since we start with an expected allocation and it's probabilistic serial, we already get some nice ex ante properties for free. In particular, ex ante endogenous we get from probabilistic serial. Everybody's eating at the same rate. We also get ex ante SD efficiency for free, which also implies ex post SD efficiency. The only thing remaining is that we want to show that every integral allocation that we get later, for example, these two allocations, these are EF1. And the trick to proving it is simply one lemma which shows that actually every integral allocation is a result of a recursively balanced sequence. So it's using one of our previous observations, and that's you're done. Apart from this result, which was positive, I also had some negative results which showed that there are combinations where things don't work out. This is better visualized in this figure. For example, this dotted line shows that ex ante SG freeness and ex ante Pareto optimality are incompatible. Similarly, these three set of properties, ex post EF1, ex ante SDNV freeness, and ex post Pareto optimality, they are incompatible as well. So this is the summary of one of the follow-up papers, and one thing that was open in Freeman et al.'s paper and also mentioned in my paper, I believe it's still open, is that ex post EF1, ex ante envy freeness, and ex post Pareto optimality, the compatibility of these three properties is still open, irrespective of the complexity of achieving it. So we don't know whether you can always achieve these simultaneously or not. So later, our two respective papers were combined into a journal paper which just got published recently in OR, and it has quite a few other results and insights as well. For example, there's one other result which was already in the EC paper, that it's possible to achieve ex ante Pareto optimality, ex post what is called proportionality up to one item, I won't define, and another relaxation of EF1, which is even weaker. This is possible to achieve via what is called an MNW lottery algorithm, which basically first finds a fractional allocation which maximizes Nash welfare. And then in order to decompose that fractional allocation into lottery of integral allocations, it needs to maintain some constraints, which it carefully does by invoking a very nice technique of Budish et al. In the 2013 paper. So this is summary of some of the results in this paper, but as is often the case in fair allocation problems, people often extend problems to the case of what is called weighted entitlements. And the idea behind weighted entitlements is that Rather than saying that every person is equal, you may also have the case that, for example, um, Juba, for some reason, he has twice as much entitlement as I do. In that case, I would not expect that I get the same value item or uh, better item. I would be fine if I get at least half of the value that I have for what Juba's bundle is. So that's a case of weighted entitlements, and that makes sense. For example, when you have families of different sizes, or you've just set some priority based on uh, some external factors. So these two papers of mine with Adi and Eva, and then Martin Häufer and some of his co-authors, they came out simultaneously in 2023, last year. And what they did was they tried to see how much the results for the unweighted or the symmetric entitlement case extend to the case of weighted entitlement case. So I'll just give you a few aspects of that. One is that obviously you first need to extend the definitions of weighted entitlements. So if, let's say, some agent I has weight Wi, then rather than saying that Ui of Ai is at least as much as Ui of Aj, you also have to normalize this comparison with the weights of the agents. And similarly, you can come up with an up to one version of this definition as well by ignoring one of the items in the other person's allocation. Interestingly, there's a reason for considering.
Actually, sorry, there's a question that I missed that Smega was asking in the chat. It was a while ago, but she was asking if she randomly chose the order for the round robin, is it still going to be X ante and V3? Or sorry, is it going to be X ante and
Yeah.
V3?
So that's I should have I was about to explain random serial dictatorship in detail and I just skipped it, but now that's another reason to come back to it. So even if you have n agents and n items and you choose a permutation uniformly at random and you allocate the items, what is interesting is this was already in Bogomolai and Mulan's 2001 paper. They showed that this particular method, random serial dictatorship, is not ex ante envy free. So it's not even ex ante envy free. Although it sounds you expect it to be quite fair. Procedurally, it looks very fair as well, but it does not give you ex ante envy fairness. So that should because random serial dictatorship is equivalent to round robin, randomized round robin for because you're just allocating n items. That also shows that this randomized round robin is not going to give you envy fairness ex ante. Hope that answers your question.
Yeah, thank you.
Right, so I just mentioned that we can have weighted version of EF and weighted version of EF1, but in fact, there's a longer hierarchy of concept that you can consider, where you can consider two even weaker versions of weighted EF1, which are called WWEF1, which is even weaker, and also what is called WEF1T or weighted EF1 up to transfer, where not only do you remove some item from consideration, you actually add it to the person who is envious. So that's helping that person even more to like finish that envy. So I don't expect you to quickly digest all the four different versions quickly. Main idea is that you have a weighted version of EF1, which is the top one. And there's a weakest one, which is the last one, where you take an item from one person's bundle and you move it or transfer it to the other person's bundle. This is the weakest version. And in between these two, there are two which are sandwiched among the top and the last one. So the reason behind considering all these versions is that if you consider just weighted EF1, which is also can be targeted from an ex ante point of view, the combination of weighted EF and any of the two middle concepts ex post is actually impossible. This is quite surprising because it's contrasts with the fact that EF with ex anti EF and ex post EF1 were compatible in the equal entitlement case. That's not the case when you take things further and consider weighted entitlements. So the first result was that even for the case of two agents, X anti-weighted EF and X post WWEF1, they are incompatible. On the other hand, as far as X anti-weighted EF and X post weighted EF1 up to transfer is concerned, those two properties are compatible, and that's just based on extending some of the key ideas I had in my paper, where you take a probabilistic serial outcome where people eat at uniform rate. Now you let people eat at a rate which is in proportion to their weights. Once you get this weighted version of probabilistic serial outcome, then you need to decompose it, and you can do it carefully. The analysis is a bit more careful. You need to look at it carefully, and you can, in a similar way, prove that those outcomes are weighted EF1 up to transfer. So this, I'm just going to check how I'm doing with time. I won't go into too much detail on the second part of this talk, but hopefully you'll get a little bit of an idea of some of the things that we've been up to in our group, which is revisiting this best of both worlds fairness paradigm in the context of committee voting. So let me just, hopefully in 10 or 15 minutes or so, I'll try to give you at least a high level idea of some of the work that we're doing, so that we have at least some time for some possible questions. So the setting I will not define formally. It's a very simple setting where you have a set of voters, you have a set of candidates, and you also have a specified number of selections that you wish to make. In this case, the number of candidates is 5. There are all these pets or potential pets that some big household wants to get, and then there's these 9 voters, and there is these 3 selections that have to be made. And these selections are based on the submitted approvals of the voters over the candidates. So for example, the first voter in blue, that particular voter just approves of the first 2 cats, whereas the last voter, it approves of the first cat and the last dog. So based on these approvals, what we're trying to do is we're trying to select a certain set of candidates, in this case, some animals. So this is what the setting is. Formally, each agent approves of a subset of candidates. There's a set C of candidates. There's a set of voters. And there's a target K, which is the committee size or the selection size. And the goal is to select an integral committee of a particular size. Now, in order to argue about what exactly is fairness in this context, for example, in the allocation context, we started with this very clear idea that in what we are after envy fairness. What exactly is a fair outcome in this context is an interesting question. There are many different approaches taken by people in social choice theory. And one particular approach that I myself was involved with some of my collaborators is what is called justified representation, which is based on this idea of people who are cohesive in terms of having a large enough size and also large enough preferences which are aligned, then they should get some representation in the committee. So a set of voters N star is said to be L cohesive if the size of that set is at least L times N over K, where N is the number of voters, K is the target committee size, and is the case that the intersection of all these agents or voters approvals is at least L. Now, in this case, for example, the 3 voters in blue, they are one cohesive. And the reason behind this is that they are at least 1/3, right? They're L times N over K, which is they at least size 3, right? And they all have at least one candidate in common, which is the first cat. So for this reason, we might say that these 3 people, because they are large enough, they are at least 1/3 of the total number of voters, and they all have some very clear idea that they all want a cat, the first cat, then they should have a right to at least select some approved candidate which they like. So this is the idea behind L cohesive, and this L cohesive was used to define what is called justified representation, which says that whenever you have one cohesive group, which is a group of size at least n over k, who approve of a common candidate, then some voter in that group must have an approved candidate in the committee. So in this example, what we're requiring is that the set in blue is one cohesive, and because they are of size at least 3, they all have a common candidate that they like. In that case, at least one of these blue voters should get some candidate that they approve of. So the requirement is that either the first or the second cat needs to be selected for this requirement to be satisfied. This particular requirement was also, there's a stronger version of it, which is called extended justified representation, which was also in this paper with Marcus Brill, Vince Konitzer, Edith Elkin, Rupert Freeman, and Toby Walsh, which later was published. First, it was a AAAI paper, then published it Social Choice and Welfare. And this particular property, it said that if you have an L cohesive group, then there should be some voter who gets at least L approved candidates in the selected committee. So these are axioms which are carefully identified and designed for the integral committee case, which is the ex post case. And the reason why they were defined like this was that we want to ensure that you can guarantee the existence of a fair outcome. Just like EF1 guarantees the existence of an EF1 outcome, similarly, what we showed was that there are some rules which satisfy EJR or JR. In particular, we showed that there's a very classical rule which was NP hard to implement, which gave you the EGR argument. Then later, some natural and simpler rules have been proposed, which give you this EJR guarantee. In particular, this method of equal shares rule is a very natural rule, which has been applied in certain multi-winner contexts in different town councils in Europe, which guarantees the existence of which gives you an EGR committee in polynomial time.
Sorry, can I ask you just a question about this definition in this slide? The
Yeah.
L approved candidates don't have to be the L common candidates, right? In that definition.
No,
Okay,
they
so
don't.
just want to make sure.
They don't have to be. In fact, if you require, so we played around with this definition. Then if you require the L approved candidates, L common candidates, you don't get guaranteed existence.
Okay, I see. Okay, makes
Yeah.
sense.
So
Thanks.
there are many versions of it. Basically, we played around and we identified strong enough properties which are still guaranteed to exist. That was the work in the axiom side. So I won't go to detail on how MES works. It's a very natural way of doing things where you think of people having a certain budget which they spend on buying, sort of buying, not actually buying, but pseudo buying candidates and so on. So this particular field in voting has proceeded quite a bit. There are many papers nowadays, both in context of multi-winner voting and also even more general context of participatory budgeting, where you even have actual costs for projects and you have a certain budget. But the focus was mostly on the ex post side, where we were focusing on naturally on guarantees which are for actual outcomes. So there's even a book now, which is by a very nicely written book by Martin Lackness Scarron, which has a summary of many of the things that have happened in the last few years. But the field is very fast moving. So I think this book came out 2 years ago, and already there are further developments happening. The main observation I wanted to make was that none of the methods guarantee agents some representation because they are deterministic methods. And this is not a design flaw of these rules or these nice properties or rules that people, very clever people are coming up with. It's just a consequence of the integrality and the determinism of the mechanism. And this is a similar kind of drawback which happens in the context of NV allocation, NV free, where let's say if you have two agents in one item, any NV free allocation, there's no allocation will be NV free, right? Similarly, if you have two agents and two candidates and only one candidate needs to be selected, and these two voters have opposing preferences over these candidates, then obviously if one candidate gets selected, the other will feel that they're not represented and so on. So any deterministic algorithm, it's not a design flaw of some clever algorithm, it just cannot guarantee representation to voters. And obviously, if you're going for nice ex ante guarantees, you might want to say that at least every voter should have some chance of getting their candidate selected, at least if you care about proportional representation. Obviously, proportional representation may have some, in political decision making, it may have some um, problematic issues where some very fringe group you might not want them to get any guarantees, for example, you may want to be very safe. That's a debatable issue, but as long as you care about proportional representation, you may want to satisfy this property. And if you do care about ex post guarantees where only safe choices are made, you can also impose ex post guarantees. Ex post, for example, you might want to say that it's ex post JR or ex post EJR, for example. So it's really up to our design choices what fairness properties we're imposing ex ante and what properties we're imposing ex post. The main thing is that before this work of ours on best of both worlds fairness in committee voting, all the attention was on ex post guarantees. What we want to do now is we want to combine ex ante guarantees with the existing literature on ex post guarantees. So when we visited this issue, obviously we want to first set up the machinery of randomized fractional committees, which is similar to what you have this fractional allocations. And a randomized committee is simply a probability distribution over integral committees. So this particular fractional committee can be implemented as a lottery over integral committees. So the kind of outcomes we are going after are randomized committees, which are probability distributions over integral outcomes. And we also want to achieve some fairness properties, which are nice. And some of the fairness concepts that we explored were based on extensions of some work I did with Anna and Hervé in an EC 2020 paper called Fair Mixing. But that particular paper was only on ex ante guarantees for essentially voting, which is just committee voting of size 1, k equal to 1. One example was this idea of fair share, which says that each voter, since there are n voters, each of the n voters should have at least 1/n of the share of the decision-making power. So she should ensure an outcome she likes with probability at least 1 over n. One way to formalize this in terms of fair share, individual fair share, is that you need to have some utility guarantees over agents, where utility is just in terms of agents having utility 1 for things they approve and 0 for candidates they don't approve. And one thing was that for agents, utility should be satisfying this particular inequality, which is 1/n of the minimum of k and the size of agent I's own approval. So that's one property we explored. You can also define a general version of it called group fair share, where you take a group of voters, set S, and the sum of the probabilities of all candidates that are at least selected, that are at least approved by some person in that set is at least 1/n times this term that we have in this inequality, which is summing over minimum of k and size of agent I's size, approval size. So these are two definitions that we explored. And what we showed was that there exists a polynomial time algorithm which computes a randomized committee that is ex ante GFS and it's ex post EJR. And it also satisfies another axiom, which I won't go into detail because there are many different axioms that you can explore in the context of both ex ante and ex post proportional representation. This particular algorithm is taking a more refined view of the method of equal share. First, it runs there to ensure that you do have an EJR outcome, and then the voters, they spend their remaining budget on outcomes that they like. And what we show is that by some analysis that this particular fractional committee satisfies GFS. We also got exposed EGR guarantee in any case, and you can use some suitable rounding scheme to decompose a fractional committee into a convex combination of integral committees. So this was one of our key results. There's some other results as well. I don't want to intimidate with too many technical fairness axiom names, but basically we've been exploring, just like in the context of item allocation, you can still start playing this game where which sets of properties are compatible and not. Some of it has been explored in some later work with a couple of postdocs in our group. Jeremy Wallen, my PhD student, and Mashka Suzuki, just an EC paper which came out this year, which takes it even further and explores even stronger ex-ante properties and achieves some of these properties simultaneously. So it's another best of both worlds follow-up paper. So just to summarize, for example, they came up with a very strong ex-ante concept called GRP. And this GRP concept is based on a network flow view of people sending in flow to candidates that they like. And when you view this as a network flow or a flow network, you can get a corresponding definition of fairness, which is quite nice. And it's stronger than many of the fairness concepts that have been explored. So this is some of the state of the art on this best of both worlds in committee voting. For example, the latest result was that this GRP, a very strong notion of ex-ante fairness, in FGR, which I did not even mention before, a very strong notion of ex-post fairness, they are compatible. So as far as open questions are concerned, I think I'll mention a couple of technical open questions. One was for allocations, ex post Pareto optimality, ex post EF1 and ex ante EF is open. Similarly, for approval-based committee voting, can we achieve something which is ex ante fair in GRP or fashion code and polynomial time? That's not a best of both worlds question. It's just a question of whether you can achieve something stronger than GRP in an ex ante sense. That's also something which is quite interesting. But more than these technical questions on these particular application domains, such as allocation or committee voting, I think the thing that we really want to advocate is that there are some nice results in the literature which are on ex ante fairness. Then there's often work which is completely divorced from that, which is on the ex post side. I think there are some nice things which come up, or some nice fundamental questions that come up when you explore the compatibility of properties, both ex ante and ex post, which opens up nice research ground, which we as people working in axioms or algorithms can explore, both from the point of view of guaranteed existence and also from a computation complexity point of view. So on that note, I wish to end this presentation. I just wanted to make sure that I'm advocating this paradigm of best of both worlds fairness, and I've convinced you that if you have some other direction, some other matching context, or some other combinatorial decision-making context, where you have some very nice insights from one perspective or the other, can we also go to the other side and also achieve the other direction as well? Thank you for your attention, and thanks to Juba for the invitation.
Oh, thanks to you for a great talk. Yeah. Okay, so we can take like maybe just like 5 minutes of questions right now, if people, but I think like everyone is kind of running. Well, yeah, does anyone have questions right now? Then I guess I mean, it's pretty much time anyway. So let me stop the recording. Like, thanks, Harris, again for the great talk. Thanks everyone for coming.